I hope my screen is visible, right?
Yeah, it is.
So yesterday we talked about some terms, right?
Yeah.
So we talked about weight.
Hmm.
What are weights, right? We talked about bias.
Bias.
We talked about forward propagation.
Yeah.
Let's forget about this for as of now.
Optimizers.
Input layer,
Hmm. Hidden layer.
and hidden layer, and then activation
Hidden.
function,
Yeah.
and then loss functions,
Hmm.
and then optimizers, and then updating the weights.
Yeah.
Now these terms, starting from bias, starting from weight
Hmm.
till your activation function, these are the part of your forward propagation,
Hmm.
and these three are your backward propagation.
Okay.
So these were the neurons,
Hmm.
right? This is your neural network. So we will see all the combinations, right?
Hmm.
Going for all the combinations. This is your x1, this is your x2, this is your x3. This is what? This is nothing, your input layer, right? Input
Yeah.
variables basically.
Hmm.
Input layer, hidden layer, output layer. Here you have y hat, then you have the loss function which is y minus y hat, right? Here you have biases plus weights,
Yeah.
w1, w2, right? And then in every neuron, two things are happening. First one
Hmm.
is summation of xi wi, which is nothing, x1 w1 plus x2 w2 plus
So
x3
on to the
w3
bias. Hmm.
plus bias. And second is activation function.
Activation function.
So let's talk about sigmoid activation function we have. So what
Yeah.
is happening in this? 1 upon 1 plus e raised to power minus
Minus y.
this term.
Yeah.
These are the things which we read yesterday.
Hmm. Yeah.
So when we are going from here to here, this is my forward propagation, right? So in forward
Yeah.
propagation, only these two things happen, XIWI and sigmoid,
Hmm.
right? Here you calculate the loss, and then comes the concept of backward propagation. So today we are going to discuss about backward propagation.
Okay.
So what happens in the backward propagation? Forward is straightforward. So we don't do anything. Simply this
Hmm.
calculation is happening, applying the activation function and calculating the loss. Only this is happening in the forward propagation.
Yeah.
Now the actual mathematic happens in the backward propagation. Now in backward propagation, it's a two-step process. First one is updating the weights, which is called as weight updation formula.
Hmm. Okay.
Weight updation formula. Because when we are updating the weights, so there should be some formula, right, by which we can update the weight. We
Yeah.
cannot randomly put any weight, right? And second is chain rule of differentiation. Chain rule of differentiation. Okay,
Yeah.
now starting with the first point, weight updation formula. So what is the formula? Very important. So you will be very frequently using this.
Okay.
W new weight new, basically the new weight which you want to calculate. For
Hmm. Yeah.
example, I want to calculate W1 new is
Okay.
equals to W old minus eta. This is your learning rate eta.
Hmm.
Yesterday I showed you on the website, right?
Yeah.
On the playground.
Yeah. I remember.
Derivative of loss divided by derivative of W old. This is the same derivative which you have read in class 11th or 12th also.
Okay.
This is called as derivative of loss, derivative of W old,
Good. Hmm.
right? This is your
Hmm.
formula. Now, let's suppose you are completed with the first iteration where you have completed with the forward propagation here, right?
Hmm.
You find out that loss is still there, right? Loss is there.
Hmm.
Now what you will do? You will update the weights. So you will update all the weights, W1, W2, W3, W4, W5, and W6. You will update all the weights, right? We are not doing this manually. I mean, we are only passing the optimizer, and it is the role of the optimizer to
Hmm.
suggest what should be the weight, and it automatically updates the value in the Jupyter notebook, right? We are
Okay.
only discussing how it is working at the back end.
Okay.
Let's suppose you want to update this W6, right? So it is nothing. W6 new is equals to W6 old minus eta of delta of derivative of loss divided by derivative of W6. This is your
Hmm.
learning rate. Now, how these values are updated? So we have talked about gradient descent, right? So what is gradient descent? In logistic regression, you must have read about this graph, gradient descent. This is nothing. This is a slope where we have to reach to this global minima. This is my global minima. My
Okay.
ultimate aim is to reach here, right? This is on y-axis, I have my loss function. On x-axis, I have my weights. So I have to minimize my loss, right? I have to minimize my loss. How, when my loss will be minimized? When I'll reach to this point.
Yeah.
Because on my y-axis, I have the loss function, right? So I have to minimize this, right? So what happens? Let's suppose your weight value is this one. Currently, your weight value is this.
Mm.
So you will check the slope of your weight. What is the slope of your weight? So in this case, the slope is what? The slope is negative slope.
Yeah.
This slope is negative slope, right? And here is your
Mm.
weight value. Current your weight value is here, then obviously you have to increase your weight to reach to the global minima, right? So you will
Yeah.
increase your weight. If your weight value is somewhat here, in that case, the slope is what? The slope is positive slope. This is your positive slope,
Yeah.
right? So here
Mm.
is your weight value, and here
Yeah.
you have to decrease your weight to
Decrease.
reach to this global minima,
Yeah.
right?
Mm.
Now, this is what? This whole term is called as slope.
Yeah. Okay.
This whole term is called as slope. If I put this slope value into my formula, so what it will be? W new is
MX
equals to,
plus. Mm.
no, W old minus eta of, if it's a positive slope or if
Mm.
it's a negative slope. So this term will be negative.
Yeah.
If I have negative slope, then this whole term will be negative.
Mm.
So this is what I'm writing over here.
Mm.
Minus eta of any negative term, right? Which comes out to be W old, negative becomes positive. When we
Mm.
multiply two negative terms, it becomes positive.
Yeah.
So it will be W old plus eta. In this case, my W new will be greater than W old. This is what we are saying. In case of negative, this is my negative slope. Here also we are saying that it should increase. And here also I'm saying my new weight will be greater than old weight,
Yeah.
right? In
Yeah.
the same case, if we have the positive slope
It will reduce. Yeah. Lower.
minus eta of positive value. Now this is what? Minus W old minus eta. So in this case, my W new will be less than W old, right? The same thing what we are saying, if the slope is positive, then in that case we will decrease it. The same thing we are saying, my W new will be lesser than the W old.
Mm.
Now how much less, that will be calculated by my optimizer
Wait. Update.
mathematically.
Mm.
And this learning rate, what should be the value for this learning rate? This learning rate, we always take a smaller value of this learning rate.
Okay.
This always remains a smaller value. Now what is the definition of smaller value? Smaller value means 0.001 to 0. I mean, if you pass the learning rate as 10, then also it will not give you any error. Yesterday we saw that, right? So when we
Yeah.
gave that learning rate too high,
Mm.
so it was not converging. Instead of decreasing the loss was increasing, right? So the reason is simple. See, learning rate means how frequently you are reaching to the global minima. If I talk about the about in this image in gradient descent, right?
Mm.
So let's suppose your weight is here, right? You have calculated a slope. Slope will tell you the magnitude, right? But what should be the step size? How frequently you are coming to the global minima, right? That will be decided by the eta learning factor,
Okay.
right? If your value is too small, right,
Mm.
then it will come slowly downside,
Yeah.
very slowly, and it will reach here, right? But if you are giving very high value, let's suppose 10 value, so what will happen? It will come here, then it will go here, then it can come here, then it can go here, then here. It will start jumping here and there randomly. So try to relate this learning rate with this
Mm.
thing. Let's suppose whenever new batch starts, right? So what tutor does? So he starts slowly in the starting, right? So that the students who are from non-technical background and are from the technical background all can cope up with the programming language,
Okay.
right? So take this one only, take this example only. So learning rate should always be small. Now interviewer generally ask, why do we use this learning rate? What if we remove this learning rate, right? So the answer is simple. So in that case also the same thing happen. If you remove this learning rate, then this derivative of loss, this value will be some big value,
Mm.
right? It can be, let's suppose 15, 20, 15, 20, 500, any value can come, right?
Yeah.
And you are subtracting weight from this, it can be anything, right?
Okay.
So to decrease this number, right, we
Mm.
use this learning rate basically,
Okay.
so that there should be some stability in my model.
Okay.
This is basically weight updation formula. This is called as weight updation formula in backward propagation, right? Now second is chain rule of differentiation. Any doubt in this weight updation?
No. Mm. No.
Okay, now next is chain rule of differentiation. Chain rule of differentiation. We are continuing with the weight updation formula. So what is my weight updation formula? It is W4. Let's suppose I want to update the weight for W4, right?
W4
Take
old
this.
minus. Yeah.
So this is my W1, W2, W3, W4. The output which is coming from this is O2. The output which is coming from this one is O1, right? This is my neural network. And here are X1, X2, X3. I want to update W4. After first forward propagation, I want to update W4. So my formula will be W4 new is equals to W4 old minus eta of derivative of loss divided by derivative of W4 old, right? The
Yeah.
chain rule of differentiation says, let if you have to calculate this thing, if you have to calculate this thing, right? So what is this? Derivative of loss divided by derivative of is equals to derivative of loss divided by derivative of O2, and O2 is dependent on derivative of W4. Now how is it coming? See, you want to calculate derivative of this one, this slope, right? So it is nothing. Derivative of loss is dependent on O2, whatever the output is coming from here, and this
Mm.
O2 is dependent on WO4,
Okay.
right? Similarly, if I ask you to update W1, if I ask you to update W1, so the
Mm.
formula will be W1 new is equals to W1 old minus eta of, right? Now you have to find this one, derivative of loss divided by derivative of W1 old. Now how I will calculate this W1 old? Can I say derivative of loss is dependent on derivative of O2 multiply by derivative of O2 is dependent on derivative of O1
Yeah.
multiply by derivative of O1 is dependent on derivative of W1. This is my chain rule.
Okay. Okay.
Very good point.
Yeah. Yeah. I got it.
Now let's complicate the things a little bit, right?
Okay.
Instead of this easy neural network, let's take some complicated neural network.
Mm.
The neural network is something in this way. This is my input layer. So this is my y hat, the output which is coming from here. This is my this is my x1. This is my x1. This is my w1. This is my o. The output which is coming from here is o11. This is my w2. This is my w3. Right? The output coming from here is o21. This is my w3 after this w4. This is my w5. Output coming from here is o22. And this is my o31. Try to understand this what I'm doing, right? So this is my
Mm.
neural network.
Okay.
X1 input. This is my weight 1. Now the output which is coming from this neuron is
Mm.
O11. This is my
Mm.
weight 2, weight 3, O21, O22, W4, W5, O31, and here it is O.
Okay.
Right? This is my neural network.
Mm.
Now here I want to update W1 new, this one.
Okay.
So how can I write this? I have to update W1. So it will be W1 new is equals to W1 old minus eta of derivative of loss divided by derivative of W1 old,
Old.
right? Now I want
Yeah.
to calculate this thing. How can I write this? Yeah, tell me. Can I write derivative of loss divided by derivative of,
O11.
start from the back, no? Start from the
Okay,
back.
so
My
O31 directly.
output, my loss is dependent on, loss is calculated at the end, right?
Yeah.
My loss is dependent on O31.
Okay. So for any of the weights, you'll have to start from O31 itself, right?
Yes, for any of the weight, we'll be starting from the last, because try to understand what we are calculating. We are
Yeah, yeah.
calculating derivative of loss. And where is the loss? Loss is this one, right? At the end.
Yeah, I get it. Okay.
Yeah. Derivative of loss divided by derivative of O31. Correct?
Hmm.
Now O31 is dependent on what? O21.
O21 and O. Yeah.
Derivative of O31 is dependent on derivative of O,
Two.
and O21
O11.
and O11 is dependent on derivative of W1, which we
Hmm.
have to calculate. This one,
Yeah.
W1 old, right?
Hmm.
Now you must be wondering why we have not considered this W4, why we have not
Got
considered this
it.
W2, right?
Yeah.
So don't worry about it. We can consider that also.
Great.
So if we write, so it will be derivative of O31 divided by derivative of W4,
Hmm.
derivative of W4 divided by derivative of O21. You can write in that way also,
Okay.
right?
So
Basically,
when we
this is
come
dependent
to,
on this, this is dependent on this, this is dependent on this, this is dependent on this. This is the chain rule, right?
so when we try
Now,
to upgrade the, I mean, W3 and W5, then we considered the output to 2, right? Because
no, no,
that's
no,
also
no. Here
dependent on
also, here
output.
also, here also here also we will consider. So it is the first part only of this, right?
Okay.
We'll do plus.
Oh,
Now,
okay.
if you see, my O31 is dependent on 2, right? So I
Hmm.
have to reach here, W1. To
Okay.
reach to the W1, I have O3 in between,
Hmm.
and O3 is dependent on two weights, W4 and W5,
Yeah.
right? So as of now, I have considered only first path, this path.
Hmm.
Now I'll take this path also,
Yeah.
right? So it will be plus. Here it is plus derivative of loss divided by derivative of O31. Now this time I'll take derivative of O31 divided by derivative of
O22.
O22 divided by
Okay.
O11.
O11.
Derivative of O11 divided by derivative of W1. This is your final equation.
Okay.
If it would have been one more neuron in this way, then you will consider that neuron also, right?
Hmm.
So this was about the backward propagation.
Okay.
Very important concept. So in backward propagation, we have uh, two things. One is weight updation formula. One is chain rule of differentiation. When I say
Hmm.
weight updation formula, this is my weight updation formula. This
Hmm.
whole term is called as
Great.
slope,
Okay. Yeah.
right? This is called as derivative of loss. This is called as derivative of the weight, whichever
Hmm.
weight you are considering. This is your learning rate,
Yeah.
and learning rate should always be smaller value,
Yeah.
right? This is what gradient descent is. What this is your optimizer, right?
Okay.
This one. So in backward propagation, we are supposed to discuss three things, right? Loss function,
Hmm.
optimizer, and updating the weights,
Yeah.
right? So we have discussed updating the weights. Optimizer is what? The gradient descent.
Gradient descent.
And loss function is what? Y minus y hat.
Yeah.
Apart from this, we have other loss functions and optimizers also. We have a
Okay.
complete list, right?
Okay.
We'll be discussing that also. But for a starting point,
Hmm.
these are the 3 points which comes under the backward propagation. And
Okay.
using these examples like gradient descent and y minus y hat as a loss function, we have discussed how backward propagation is done.
Okay.
For activation function, for loss function, for optimizers, we have a complete list.
Hmm.
We have other activation functions, other these things also.
Loss functions also. Yeah.
Okay, now a very important concept we are going to discuss now, which will definitely come in the interviews.
Okay.
Vanishing
Gradient descent.
gradient, gradient descent. This gradient descent.
Hmm.
Now,
Okay.
vanishing gradient descent. This problem was so major that in 2000s, 2001, 2002, right?
Hmm.
Scientists stopped the working on neural networks, right?
Okay.
Because whenever they were building the model, using the neural network,
Mm-hmm.
right? The performance was not increasing, the loss was not decreasing. Whenever they were taking the small neural network, right? Small
Mm-hmm.
neural network means less number of hidden layers. Then it
Mm-hmm.
was working fine. But if they
Okay.
are increasing the hidden layers, but
Mm-hmm.
if they were increasing the hidden layers, so in that case, my model was not learning actually.
Okay.
If the loss was zero point 0.6, it was still the zero point 0.6 even after so many epochs.
Okay.
So the reason was simple, because weights were not updating,
Mm.
right?
Okay.
Because if weights are not updating, then obviously the loss function will remain same. No?
Yeah.
What happens in this case? In forward propagation, we calculate here loss function, right? After loss
Mm.
function, we update the weights, no?
Yeah.
If weights are not being updated, then obviously the loss will remain the same.
Mm.
This was the problem,
Okay.
right? Okay, now let's try to understand this vanishing gradient descent. Very important. Okay, so you can make a note of this.
Okay.
Let's suppose this is my neural network. This is my deep neural network, right? In
Okay.
which I have one, two, three, four hidden layers. So this is my input layer, X1. This is my W1, weight 1. This is my W2. This is my W3. This is my W4. And this is my output, right? Which is Y hat. Correct? Here I have bias 1, bias 2, bias 3, bias 4, and bias 5. Here my output is O11, O21, O21, O31, O41, O51. Is it clear till now?
Yeah.
What we have done? Neural network, but this is deep. As of now, we were
Mm.
discussing only smaller one, right? Where we have two hidden layer or one hidden layer. But in this case, I
Mm.
have these many hidden layers, right?
Okay.
Now, I want to update this W1. After my first iteration, I want to update this W1. So
Mm.
can I write using chain rule of differentiation? How will I write this? W1 new is equals to W1 old minus, speak up, minus
Eta of
theta,
TL by TW. Dif- old.
correct, right? So this will be
Yeah.
my weight updation formula. Now I have to calculate this thing slope.
Yeah.
So what is this? Derivative. Don't call it d, this is derivative.
Oh,
Derivative.
yeah, yeah,
So
yeah.
whenever you are going to speak this in interview, also call it as derivative.
Okay.
Derivative of loss divided by derivative of W1.
Right.
And this is written
Okay.
in this way, not a simple in d form. No.
Yeah, like
This,
partial differentiation.
yes, correct. Correct. W1 old is equals to. So in this case, what should I write? Now tell me. Chain rule of differentiation. It will be
Derivative of loss by derivative of O51 output 5
perfect. Multiply
into
by,
derivative of O5 I depends on O41
good.
into derivative of O41 by derivative of O31 into derivative of O31 by derivative of O21 into derivative of O21 by derivative of O11.
Uh,
And
we have
then
to update weight 1. So do you think we
so
need to
you
go
want
to
to
the
stop.
O11,
Okay.
right? So we have to reach
Mhm.
here, W1. So can
Okay,
I
so
write
we have to solve.
O21
Okay.
divided by derivative of
Oh,
O1
wait, yeah.
up till this point,
Okay.
right? Now, what is happening? So we want to go back, right? So
Mm.
yesterday we talked about sigmoid function. Let's suppose sigmoid
Mm.
function is used in all of these.
Okay.
And earlier only up till 2000s, right? So only sigmoid function was available, so they were using only the sigmoid function only, right?
Mm.
And this problem arises due to that only, sigmoid function. So if I talk about sigmoid function, so I told you like the value ranges between 0 to 1,
Mm. Yeah.
right? Maximum value will be 1, minimum will be 0, so value will be
Mm.
0 to 1.
Yeah.
But this value is 0 to 1 when you are going in the forward direction,
Mm.
correct? But when you are going in the backward direction, then we'll have to calculate the derivative of this also, right? Derivative of
Yeah.
your sigmoid function also. And the
Yeah.
derivative of your sigmoid function,
Mm.
it is nothing. Let's suppose this is your sigmoid function. Value is 0 to 1,
Mm.
right? And derivative of sigmoid function will be 0 to 0.25. This value will be in between 0 to 0.25,
Okay.
right? And the chart for this This is your sigmoid function where value is 1 to 0, right? So
Mm.
for derivative, the value will be 0 to 0.25. So this is your 0.25.
Okay.
Maximum value will be 0 to 0.25. Are you getting why we are doing the derivative of the sigmoid function? Because we are
Yeah,
going
yeah.
back,
Yeah,
right?
I
We are
understood.
going back. Now,
Mm.
in this case also, we'll be having in between 0 to 0.25. Let's suppose here we are getting 0.25 maximum value.
Mm.
In this, we are getting 0.20. In this,
Mm.
we are getting 0.22. In this, we are getting 0.15. In this, we are getting 0.10,
Okay.
right? For example, right? These are the different values we are getting, right? And in all
Mm.
of these, we are using sigmoid function. This also, here we have sigmoid, and sigmoid
Yeah.
activation function, right? And we are using sigmoid activation function, so maximum value will be 0.0.25, 0 to
Mm.
0.25. Now, when you multiply all these terms, so the value will be very small, right? Because it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it will be 0.00008 times 0 and then some value
Okay.
268. Now, what you are saying to the model that this value, when you insert this value into your equation, into
Mm.
this equation, W1 new
Mm.
is equals to W1 old minus eta of very small number,
Mm.
very small number,
Yeah.
right? Now, what is this? Eta is again a small number where it is 0.01 or 0.001.
Yeah.
You are multiplying very small number with the small number. It is again a
Mm.
very, very small number
Mm.
minus,
So it's almost negligible amount of difference in the weight.
yes, yes, exactly. So basically you are subtracting very, very negligible amount of number from this, and
Mm.
your W1 new will approximately be equal to W1 old.
Mm.
So basically you are not updating the weight. So
Yeah.
if you are not updating the weight, then obviously your performance will remain the same.
Mm.
So this is called as vanishing because your gradient descent is vanishing.
Mm.
Because your gradient descent is vanishing in this case. You are not able to
Okay.
reach to this global minima.
Okay.
So this was the problem which was prevailing up till 2000, 2002. Because of
Okay.
that reason, scientists came up with other activation functions. Till this time, they were using only this sigmoid
Sigmoid.
activation function.
Mm-hmm.
So to avoid this problem, we have other activation functions. Now let's try to
Okay.
understand what are those other activation functions. So the this was the one of the problem with the sigmoid function.
Mm.
This was one of the problem, and there was one more problem with the sigmoid activation function, which was that it was giving values only in between 0 to 1. The y value was only between 0 to 1. It was not giving me any negative number.
Okay.
So in ideal scenario, what should be the case? My curve should be zero centered curve. Zero centered curve. Now, what is this zero centered curve? Zero centered curve means whose mean lies in between this, in this way. This is called a zero centered curve. In this case, I'll be getting the y value as positive also and negative also.
Mm-hmm. Mm.
See, this is my sigmoid function. In sigmoid, my y value will always be positive,
Yeah.
right? Because nothing is there below this line. But here, if you see, I have a negative value. For negative value of x, I'll be getting negative value of y.
Okay.
Here we can define the range, like if it is 1, then here it can be -1, right? Here we can define the range, but at least
Mm.
it should be in this way where we can get the negative values. So these were the two problems
Okay.
with this sigmoid activation function.
Okay.
And to overcome this problem, they came up with another activation function, which is second function, which is tan h. Tan h.
Okay.
So it solved this problem of zero centered. The curve of this tan h is something like this, and the range is from 1 to -1,
Mm-hmm.
right? So the range is -1 to, and equation is e raised to power x minus e raised to power minus x divided by e raised to power x plus e raised to power minus x. This is the equation of this tan h.
Mm.
What was the equation for the sigmoid function? 1
1 by
upon
1 plus
1 plus
e
e raised to
power
power
minus
minus x. This was the equation
minus
of
y.
this.
Yeah. Mm.
This is the equation of 10x, right?
Okay.
Now, what is the derivative of this? Because whenever you are learning any activation function, you should know the derivative also. Because
Okay.
in this, you will be calculating the derivative values only if you are
Huh.
using any activation function. So what is the derivative for this? The derivative is in this way, and its value is between 0 to 1.
Okay.
So the derivative value is from 0 to 1. In my sigmoid activation, it was from 0 to 0.25.
0.25.
In this
Yeah.
case, it is 0 to 1, right? Now, if you observe here, it solved the problem of that thing, zero
The less
centered curve,
values. Mm.
zero centered curve,
Mm.
right? But here also the derivative is in between 0 to 1. So that
Mm.
means
The value
here
might be
also the
there.
values can be 0.6, 0.7, 0.8, 0.9. If we have a
Yeah.
very big neural network, in that case also we have the problem of vanishing descent problem, right?
Mm.
In this also we can have the vanishing gradient descent problem, no?
Yeah.
If the neural network is too large,
Yeah.
if the neural network is too large, in that also it will get fail. And second disadvantage of this is, if you see this equation, this is too complex, no? E raised to
Mm.
power x plus e raised to power minus x, then e raised to power x, then again e raised to power minus x. Time complexity equation. It will take too much time to, do all the calculations.
Mm.
So
Okay.
to overcome these problems, so they came up with another activation function, which is ReLU, very important,
Okay.
ReLU, right? So in the real time also, you will be using ReLU very frequently,
Okay.
right? The full form is rectified linear unit, rectified
Mm.
linear unit. Since linear is there, so that means it will be it will be related to some straight line,
Mm.
right? Now
Yeah.
the equation is the chart is something like this. For positive value of x, y will be same.
Mm.
I mean, whatever the x is, same will be y. And for
Mm.
negative value of x, y will be 0. So the equation is, for ReLU of x, the equation is maximum of 0 comma x. Can I say maximum of 0 comma x? Means it will check if the x is positive,
Mm.
then obviously my maximum of 0 comma x will be x value, positive
Yeah.
value. If it is
Yeah.
negative, minus 5, if x value is minus 5, in that case it will be 0. The same
Yeah.
chart. This is the equation for this,
Okay.
right? If I want to see the derivative for this,
Mm.
derivative will be, for less than 0, it will be 0. For greater than 0,
Yeah.
it will be 1. Very simple, right? Here, if you
Yeah.
see, the mathematic is very easy if you
Mm.
compare this with this, right? But here also we have the problem. Here
Mm.
also we have
Okay.
the problem. In this, if our weights are 0,
Mm. And the whole thing will fall apart as well.
whole thing will be 0. Yes, in that case, everything, the whole neuron will get dead.
Yeah.
The whole neuron will get dead, right? If my weight is 0. So this again has some problem. If
Mm.
weight is 0, then in that case, my whole neuron will become dead.
Yeah.
Now to overcome this dead neuron problem, scientists again scratched their head and came up with another activation function, which is leaky ReLU.
Okay.
Leaky ReLU. So you will be doing same thing in your Jupyter notebook also.
Okay.
If you are using this ReLU, so firstly you will try to apply this ReLU activation
Mm.
function in your model. If you think like your neurons are getting dead or they are
Mm.
not learning, right? So
Mm.
what you will do, you will apply leaky ReLU in that case, right? It solves the dead neuron problem. Now, in this case, how my graph looks like in this. Now, in ReLU, it was 0, right? In case of
Mm.
x, but in this case, it will be slightly higher than x, slightly higher. For positive value, it will be x, right? So the
Okay.
equation is maximum of 0.01x. Now try to relate this. What will be my value in case of negative value? In negative number, earlier I was making it as 0, but in this
Yeah.
case, negative, it will be some value 0.01 into x.
Yeah.
And if I want to see the derivative for this, the derivative will be something like this, slightly above 0. This one. It is not exactly 0, it is more than 0.
Mm.
So this solves that problem, dead neuron problem. right?
Okay.
Okay, then fifth. So total we have 9 functions, right? So we are going to discuss. So fifth is exponential linear unit, loop,
Okay.
exponential linear unit. So for this, the equation is x if x is 0 and alpha of e raised to power x minus 1 otherwise.
Okay.
And if I talk about the chart for this, so it will be something, and this is for the derivative. This value is 1. So I'm saying if x is greater than 0, means this one,
Mm-hmm.
then the value will be x. The straight one, which the same one which was there in the ReLU function.
Mm-hmm.
And e raised to power x into alpha. So alpha can be any value,
Mm-hmm.
right? Okay. Then we have softmax function. Softmax, this is again an important function.
Okay.
Softmax function. The equation is something like this. F of x is equals to e raised to power xi divided by summation of I is equals to 1 to n e raised to power xi. So what does this mean? Let's suppose you have a neuron. These are the
Mm-hmm.
input values 4, 2, 4, 8, 1. So it will give the importance based on the magnitude. More the magnitude, more will be the value.
Okay.
For example, if I ask you to calculate the probability for instead of 8, let's take it as a 6 so that we can take the example of dice. For example, if I ask you if I want to roll a dice, what is the
Mm-hmm.
probability that I will get the 2? Can I say 1 divided by 6?
Yeah.
Can I say this thing?
Yeah.
For 4, what will be my probability of getting 4
Same.
when
One
I
by
roll a
6.
dice? 1 by 6. Same 1 by 6.
Yeah.
If I want to calculate the probability, I will calculate in this way, right? But
Yeah.
softmax is somewhat different, right? In this, if I
Mm-hmm.
want to calculate what are the chances for this, so I will say more the magnitude, more will be the value. So this will have maximum value, right? So how we will calculate this? F of 2 is equals to, I'll put in this equation, e raised to power
Mm-hmm.
2 divided by e raised to power 2 plus e raised to power 4 plus e raised to power 6 plus e raised to power 1. So when you calculate this, you will be getting some value 0.002, let's say,
Okay.
right? Then what you will do? You will calculate the 4 f raised to power 4. So here also you will have e raised to power 4 divided by e raised to power 2 plus e
Same.
raised to power 4 plus e raised to power 6 plus e raised to power 1. Now this value will always be greater than this value because the magnitude is high. 4
Mm-hmm.
magnitude is greater than high 2, right? This value
Mm-hmm.
will be greater than this. So I can say 0.3, any value.
Okay.
Similarly, I'll be calculating for f raised to power 1. For 1, I'll have the minimum value, which can be 0.00001, right? Out of these 4, the value will be minimum. And then I'll
Mm-hmm.
calculate the last value, which will have maximum probability, which can be, let's suppose, 0.7. Now, if you sum these up, right, it will always be 1.
Mm.
Summation always be 1.
Yeah.
So this will have the maximum. It is
Okay.
it is used for multi-class classification.
Okay.
Multi-class classification. Okay.
Mm-hmm.
Right. Now next is PRELU. ReLU activation function. It is called as parametric ReLU. It is saying basically y of I, or you can say x of I, if y is greater than 0 and a of y is less than equal to 0. Right. Now what is this a? This is called as learnable parameter. Learnable parameter.
Mm-hmm.
Right. Now if you compare this equation, this is very equivalent to, this is a combination of basically ReLU plus leaky ReLU.
Okay.
So what was my ReLU? ReLU was maximum of 0 comma x, right? And leaky ReLU
Mm.
was 0.01 x
0.0x.
comma x.
Yeah.
Now if you see here, y of I, if my value is greater than 0, in that case it is my ReLU function, right? If it is
Mm.
less than equal to 0, in that case it will become my PReLU. Sorry, leaky ReLU.
Okay. Mm. Yeah.
So it's a combination of ReLU and leaky ReLU. Now next is swish, and one is max out. I mean, these are not very frequently used. So, but still we can discuss. So 7 are done. Now is 8th is swish. 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 A self-gated function. It is called as self-gated function.
Self-weighted.
Self-gated. Gated?
Gated. Okay.
Self-gated function. Right. So here also the equation is a little bit complex. Y is equals to x of sigmoid of x. So what we are doing? We are doing nothing. So we have the sigmoid function, right? So this is nothing. This is your sigmoid function, and you are multiplying it with x. That's it,
Okay.
right? What is your sigmoid function? 1 divided by 1 plus e raised to power minus x. X divided by 1 plus e raised to power minus x. This is your Swiss function.
Okay.
So basically, scientists came up with this Swiss function because in sigmoid you were getting very low value in between 0 to 0.025.
Yeah.
The derivative varied, right? So to overcome that problem, they are multiplying it with x now.
Okay.
So these are different experiments they were doing, and they came up with so many different solutions. But every activation function has its own advantage and its own disadvantage. Now, next is last one is max out. Max out, right? So it is nothing. It is basically maximum of w1 x1 plus b, comma w2 x2 plus b plus w3. How many inputs are there? That many, right?
Oh,
Whatever the maximum value is there, that will come in the max out,
okay.
right? Now, how many functions we have read? See, first one is sigmoid function, which is very frequently used, very important, right? Then we have the tanh. It is again important. Next is ReLU, again important. If you are getting the problem in ReLU, you will be using leaky ReLU, right?
Yeah.
You will not be using this very frequently. You can ignore this also, ELU, but you should know, right? For experiment purposes, you can use this also,
Okay.
right? Then we have the softmax, very important. I'll be telling you like when to use which, but this is not the
Okay.
thumb rule. That will not be the thumb rule, right? It's all depend on the parameters. Then we have the PRELU, then we have the swish,
Max.
and then we have the max out. Now, when to use which? If you have a binary classification in the output, whether a person will play or not, this is your binary classification example. Here you have only 1 or 0 as the output, right? So here always try to use sigmoid function in this outer layer,
Okay.
because sigmoid always gives you in between 0 to 1, 0 or 1, 0 or 1, right?
Yeah.
And in between you can use ReLU.
Okay.
In hidden layers you can use ReLU. Let's suppose if you have 5 hidden layers, use 5 times ReLU in
Okay.
all the hidden layers. If you're finding problem in ReLU, try with leaky ReLU or
Okay.
PReLU, right? But in output always use sigmoid.
Okay.
I mean, it's not like thumb rule that you always have to use this thing, but give it a try with this. If you are not getting the good accuracy, then you can go with other functions also.
Okay.
But if you have multi-class classification, right? Multi-class in the sense you can have
More
more than
than.
2 outputs
Yeah.
in this way. There will be 2 different outputs. So
Yeah.
in that case, you can use ReLU here and you can use softmax in the
Okay.
output layer, right? ReLU plus softmax. ReLU in the hidden layers and softmax in the output layer.
People here.
And if you have the regression problem, continuous values, right? So there you can use linear activation function.
Okay.
If this is your that thing linear regression problem, here you can use ReLU in the hidden layers, right? And linear in the output layer, linear activation function. Is it clear?
Yeah.
But I am again saying this is not the thumb rule. Sometimes you can see like instead of linear. So yesterday I was discussing one example with another session where it was the example of this thing, linear regression, right?
Okay.
But this was giving me 60% accuracy, but sigmoid was giving me 72% accuracy, right? So that's why I'm again saying that this is not the thumb rule that always you will be using this. But as a general practice, we use this, we try to get the best accuracy for these with these functions.
Okay.
So this was this thing. Okay. Now let's talk about some loss functions. So loss functions are what? Which we calculate in the forward propagation at the end, right? Loss function.
Mhm.
So as of now, we were only considering y minus y hat
Yeah.
as the loss, right? But here also we have different functions, loss function. And that depends what kind of business problem you are solving, right? If it's a linear
Mhm.
regression, then we'll be using another type of loss function. And if you are using classification problem, for that we have another,
Yeah.
right?